even if it's now virtual.
I missed the big red button the chairs had in person.
And it is now 15:30, I see, so I think we can start. So this is the Mcat session, and I'm Anna Brunström, and I'm here with Colin, and we are Perkins, and we are the co-chairs. And let's see if I managed. So this is the note well. I think we are on Friday, so you're probably all familiar with it by now. If not, do read it, of course, because it does apply to the meeting. And to start with, some administrativa. So the meeting is being recorded. I think you're aware of this by now as well. We do need a note taker for the meeting. Do we have someone that can help out taking notes? Now I don't see you guys. It's harder to look at someone suitable. So Gori, you are in the queue. Gori, was that you volunteering to take notes?
Yeah, okay. I can't say I cannot do it, so I will enjoy doing it. I'll just bring that up and take notes in the Hedgehog.
Thank you. And did you want to add something else, or no? This was why you left the queue now. So great. So I think we don't need a separate Jabber scribe because we have the Jabber now integrated in Mythical. So we will keep an eye on that. So let's see. So as Colin hinted at, we have not met in a while. So this is the agenda we have for today. We're going to have an update on our algorithm. So we met last time for a meeting at IETF 106. And at this point, we decided we had delivered our algorithms and most of our documents. And we decided that we would go idle for a while to try and gain experiences with the algorithms to then come back and see how we would proceed after that. And at that point, we were thinking to go idle for about a year. But then, of course, the pandemic arrived, and we were hoping to also be able to meet in person. But now, of course, it's high time to come back and see what has happened to the algorithms and what do we have left as work in the working group. So after we finish this introduction part, we will move to looking at the update on the status of the Mcat algorithms. So first an overview of it from the shares, and then we will have Ingmar presenting some updates with the Scream algorithm from RFC 8298, and we have David presenting some updates on the shared bottleneck detection from RFC 8382. And then we have one active working group document that has been left behind on RTCP feedback for congestion control, and Colin will give us the update on that, and then we will see where we are on the different activities, how to wrap up or what we have left to work on. So to start with a recap of the working group activities, we have had 4 algorithms that we have submitted as experimental RFCs, and they have been now all published. They have been in various queues, some of them waiting for each other, but we have the Scream algorithm and the NADA algorithms, the 2 congestion controls, and then we have the coupled congestion control and the shared bottleneck detection. And the last of those, the NADA algorithm was published since we last, after our last physical meeting, and the coupled congestion control had a dependency there, so it was also published after we last met, but they were all submitted at this point in time, but now they're also all RFCs. Then we have had a set of requirements and evaluation documents. And the requirements was actually the first document that was sent for publication from the group, but that was in the queue for a long time because of the WebRTC bundle. And then most of the evaluation documents had the dependence on the requirements. So 4 of these documents were all now published in January of this year, when this whole sequence of documents were completed and all published, and we already had the video traffic models published before. And then we have one active working group document on the feedback side, and this is the draft that Colin will talk about. And when we last met, this was waiting for the RTP control protocol feedback for congestion control, the feedback message that was handled at that time by the AVT core. So that is now published in RFC 8888, and so we should now finish up this document that was depending on it. So we have that on the agenda. So this was a recap of where we were with the working group. We thought this would be good since we did not meet in a while. Any questions or comments on the general update? Otherwise, we will move on to the algorithms to have an update on those. So we have 4 algorithms, and Ingmar, you're in the queue because you will be presenting soon, I assume. So is this why, or you wanted to ask something?
I'm trying to figure out how to cancel slides request.
Yes.
Possible before isn't possible anymore.
No, it's there. I see it. I will just give the overview first, and then I let you share. So I'm on the overview slide, so no worries. So we have the 4 algorithms. So we have Scream, and Ingmar will give us the update on that. Then we have the NADA congestion control, and Xiaojing updated the status on that last year, that they had the full implementation completed of NADA in the Mozilla browser. And this was kind of the completion for them on the work. So there has, as far as the authors and shares know, there has not been any ongoing activities after they completed this implementation. And Xiaojing and her co-authors have moved on to other projects or other employees after that. So I think there is no ongoing work on NADA as far as we know, but there is the open source implementation. Then there is the coupled congestion control, and there is some ongoing research on the topic by the authors. So they have some students working on coupling the video and data flows in Chromium, but there are no results or ready things to report, but still some ongoing research. And then we had the share bottleneck detection, and David will give us the update on that. So with that, I will now stop my sharing, and I will now, I think, Ingmar, you should be able to share, and I will give the word to you to give us an update on Scream.
Okay, and this hope you hear me well, and with the audio check was okay before, and this is an update what has been done in terms of experiments and future, and about around Scream, which was developed by me and Sahed and published, or was it late 2017? It's been a couple of years since, and I can skip to the next. Okay, I need to click on number 2 here. And there are some to start with where Scream is or isn't used. And originally, Scream was intended for WebRTC, and that was the whole intent of it back when it was the work started. And it was implemented for Open WebRTC, but it never got traction, and it never really evolved into WebRTC. And so we don't, for natural reason, we don't have any much experimentation around that. So, but perhaps something that was a bit below my radar is that there was you can probably look at the AVT core presentation where Mattis Engelbart and Jori Ott presented, where I have integrated Screen with a Go Quick implementation. So they have some results there and found the issues when implementing Screen there. What has been tried more is cloud rendered gaming, and now we're not talking about 1-2 megabit per second. It's more like 30 megabit per second video with high quality, and there we have done quite a lot of experimentation. And then we also have for remote driving, where we had our remote control car that we have been driving around in various projects. And that also includes high bitrate video with multiple cameras, and also a Scream has some kind of it's a wrapper around the congestion control that makes it possible to do some benchmarking, for instance, over 5G networks. That has been done quite a lot. And about the cloud rendering gaming, and here we have been much focused around the development of L4S, and Scream was picked because it's not the perfect algorithm, I don't claim that, but it's a known algorithm, and it was quite easy to dig up statistics around how it worked and what kind of latency you got, and that later on evolved into implementing a GStreamer plugin to do as a real experiments with cloud rendering gaming. And where we were able to try the experiment with and without L4S, and it was we found a couple of issues with the Scream algorithms in the process, and mostly related to how video encoders behave, especially when you frequently update your target bitrate. And I will come back to that later. And then we have remote driving, where we have done quite a lot of experimentation, and we have other students who have integrated the Scream algorithm with a remote control car, and we have tried out in various environments and over 4G and 5G networks. And it has been a pretty good test platform to benchmark how it really behaves in pole coverage, for instance. And unfortunately, we don't have much data to show because it's a bit sloppy behavior. We run a test, and then we drop all the data, and it has been a bit of a ad hoc testing, pretty much, and for demo purposes. And hopefully we do that better later on. And then we have this benchmarking tool that is available for public use, and what it does is that it emulates a video encoder, where you can have you can pick either a fixed bit rate or you make it rate adaptive, and you can do the rate adaptation over quite a large bitrate range, from a couple tens of kilobit per second up to more than 500 megabit per second. The upper limit there is depending on what kind of laptop you are using, or the virtual machine that you have in the other end, for instance. How much because it becomes a bit CPU consuming, especially given the packet pacing and that is involved. So it's not ideal for really high bitrate applications, but up to something like 500 megabit per second you can try out. I believe the highest I got was like almost 900 megabit per second over 1 gigabit line. So, and you can also model iframes and variable frame size. So you get something that is similar to how a video encoder in a constant bitrate mode behaves, but it's not identical, of course. And you can measure round trip time, the estimated queue delay, which is by output from the Scream algorithm, the throughput that you get, both the transmitted bitrate and what is acting in the other end, and packet loss and CE marks. And it's capable of trying classic ECN and L4S. And okay. And the findings so far is that what we have found is that the window-based congestion control is, which is Scream, it is more or less actually TCP LADBAT, but with a little more bells and whistles. That is probably good, at least for cellular access, because you can have a radio recall resource configuration that happens, and you can have handover that can cause transmission pauses, cause transmission pauses. And that if that is not handled, you end up quite easily with a lot of data in the transmit buffers in the network that is just there, and it causes head of line blocking for subsequent video frames. So it's better to have it as a window-based congestion control, and then you have a lot of share of, in cases like this, you have a lot of packets in the sender that you can discard if they are deemed too old anyway. So, and then you can locally on the sender side force a new IDR. So you get quite a fast recovery because of that, and that is has been shown in the experimentation with the remote control car, for instance, where you can, in really bad coverage situations, you can end up with in those situations. And the feedback rate, we have had a lot of discussion, and Colin, for instance, have done some work around what is the applicable feedback rate that is needed. And as it is today, it's something like 1 feedback per 16 RTP packets, and that is probably overkill. And but to be honest, I haven't done so much experimentation. What is the pain limit here? It has been more focused on a stable streaming than optimizing the echo overhead. So as it is now, you end up with something like the feedback bitrate is something like 1/50 of the media bitrate. That's where you end up roughly. And the video encoder, that is something like 80% of the development work. Doing the network congestion control, that has been quite easy. But the video coders, sometimes they are really strange animals, and you have a video coder that are sluggish. When you sort of set the target bitrate, it can take a while for it to adapt to the new target bitrate. And sometimes you have that the video encoders can become confused by frequent updates. And for instance, the NVENC encoder can give a what's called a systematic offset. So if you set it to 20 megabit per second, you will get like 22 megabit per second on the average. And that has been it's not a disaster for Scream, but it's to give some kind of a suboptimal behavior, and that is not always visible if you don't if you use just endpoint based adaptation, but it's more if you use L4S, then you start to see those anomalies. And also that iframes, they are really problematic in congested situations because they can be really large. And so the outcome is that you transmit iframes only when needed, and also gradual decoder refresh, also called periodic intro refresh, can be useful if that is implemented in decoders and in the encoders. And another way that is used in a remote control car at lower bit rates is to compress the iframes even harder. You set the QP max and QP mean values to keep control of that. So there are some issues with the video encoder that even though your congestion control algorithms work like the charm, you have a video encoder. It's essentially a black box that can cause a lot of issues for you. And then we have what is to be done in the future. And currently, some kind of an L4S implementation is in running code that is not in the standard. So I have some plans to do an update, possibly based on improved L4S implementation later on. But that is not planned right now, but hopefully later on. I believe that was the end of the presentation, and 4 minutes left. And do we have questions or?
Thank you, Ingmar. So let's open up the queue and see if we have some questions. So let me ask one question on, because you mentioned that the code has the ECN support. So the results that you showed, they were using ECN feedback, or they were based on loss-based?
I believe what result we have is that so far they are in sort of unofficial, or they also to the degree that they are official is in this demo here. And here is if you probably won't see, but you can see that the amount of marked packets you see in the. Sorry. Yeah, there you can see the amount of marked packets and how it controls the bit rate of the video. That's so far it's only in that experiment that you're using in this case L4S. We haven't done much experimentation with ECN.
Thank you. We have Mo in the queue. Go ahead, Mo.
Yes, from what I understand, the original design in Scream was motivated by wireless clients. Do you think that original design is still part of the model, or do you think it would be equally optimized for things like data center to data center traffic? So I'm really wondering whether or not it makes sense to start considering the full topology when we look at the congestion controls, and wonder if a one-size-fits-all model is maybe not appropriate, and we need some tailored for specific environments.
I can say I believe the most of the focus was on the last mile 4G and 5G access. That was what the driving, but I haven't thought about the data center, for instance, if that is applicable there. And I somehow suspect that other algorithms, like if you look at the Prague or BBR version 2 or something like that, could be more applicable there. I'm not sure, but it's a pretty tailored to the streaming of RTP media in this case, and not sure how useful it is in a wider context.
Follow up, do you think that the direction matters? Were you mostly optimizing for send from a client, or were you mostly optimizing for receive from the clients?
I'm not sure if I understood the question.
Are you trying to optimize, was Scream mostly trying to optimize the transmit video of a mobile endpoint or the receive video of a mobile endpoint? Or do you think that you tried to actually optimize both directions equally?
I believe the actual Scream algorithm it doesn't really optimize. If you look at and think about the jitter buffers, for instance, that is up to for instance, a GStreamer pipeline to handle. And it doesn't do retransmissions and that stuff, and it just handles the congestion control without it's like TCP without the retransmissions, more or less. But it's a rate adaptation algorithm that is more sensitive to delay increase. And I'm not sure if that answered the question, but yeah.
Well, Mo left the queue at least, so I guess it did. Do we have any last
Yeah.
questions for Ingmar? No, if not, thank you very much, Ingmar, for the update on Scream. And then David, you're up next. Okay, we see your slides.
Okay, thank you. Well, this is an update on the shared bottleneck detection work, and thanks to Michael and Simona for their help putting this together. Oops. I have to make sure I'm on the right window, I think, before the slides move. Okay, some work that's happened probably since the last time we were here, which was quite a while ago. There's been some work putting basically the RFC version of SBD in multipath TCP and in multipath QUIC. And what we'll be talking about, what I'll be talking about today is a thorough comparative study that we've done of RFC 8382, and we recently had it published in IEEE ACM Transactions and Networking. Now what we do is we compare the vanilla RFC 8382 with the statistics that we collect, but a different type of way of grouping, a dynamic online clustering method. And then we compare that with what was one of the most promising ones in the literature, a different type of method, a cross-correlation method that originally was an offline method, and also our online adaptation of that. And in the paper, we look at teacup test bed experiments, simulations, some experiments over the internet as well. And what we will look at today is the time it takes to detect a bottleneck and to detect that the bottleneck's gone away, the effect of different path delays on how well you can detect bottlenecks, and the effect of having lots and lots of parallel bottlenecks. And of course, there's more in the paper if you want to read it. Now, the Mcat version is based on summary statistics. It was based on summary statistics because originally one of the requirements was very low feedback overhead. So with this method, we send the summary statistics not very often. And it also allows for us to detect bottlenecks on senders or receivers and work with both. It's a divide and conquer method, the one that's written up in the RFC, where and it's very simple, very light, where we take our flows and our measurements and first divide them into what flows are experiencing congestion and what are not. Then we take that group and subdivide it according to an estimate of the oscillation. Then we look at the sort of variance, how they vary as a summary statistic, and then an estimate of the skew. And then if the packet loss is high enough to be statistically relevant, then look at packet loss as well, dividing into smaller and smaller groups till we end up with the final. The most common question we were asked is, why don't we use a clustering algorithm? And that tends to be difficult because we don't know the number of groups. The number of groups keeps changing and the flows in each group can keep changing. But we have got a novel iterative one that we present, and it sort of does the closest neighbor by an inverse square law. Now, the other main way of doing this sort of thing is to correlate the different flows. But because one-way delay is so noisy, if you don't use summary statistics to help with the noise, then you need to filter it some way. And this uses wavelet filtering techniques, which are easily implementable in an online way as well. But the original one takes the whole delay trace of every flow, puts it into MATLAB and gets MATLAB to work out what the optimal filter characteristics are for the whole of everything. So you need a crystal ball for this one, and then filters the trace and then does pairwise correlation coefficients. Okay, our version, a slight modification of that, works out when's a good time to estimate good filter coefficients and then estimates them on the fly. Okay, firstly, looking at detection delays. So how long does it take after a bottleneck starts? If we know ground truth, then we did in this experiment, before we can say there's a shared bottleneck. And then after it goes away, how long before each of these algorithms can say it's stopped? And it's not that surprising that the offline crystal ball method in green works out the start of bottleneck very, very quickly. It's not so good at detecting the end because it was never designed to do anything but detect bottlenecks, not stop them. Our online version of that in yellow also is similar, not quite as good because it's not optimal, I suppose. Then we have the RFC based ones. The DCSBD is the clustering, dynamic clustering one, and the Mcat SBD is a straight RFC. And you can see that the summary statistic ones introduce some lag, and it takes, up to about 4 seconds, sometimes more, to detect or the start or a stop of a bottleneck. Now what we did here is different paths have different delays. So if all of the paths that the flows are going on have exactly the same delay, then the source lag difference we say is 0. But if the difference between the flow with the shortest transit time, propagation delay, and the longest propagation delay is 1,000 seconds, then in here the source lag difference would be 1,000. And what you see here is as the difference between the propagation delays of the different flows increase, the summary statistic methods handle that very well. But the correlation ones, the more lag we get, the less well they handle it. And you can see that by the efficiency. We use the F1 score for accuracy in this case, which is sort of a harmonic, is the harmonic mean of precision and recall. But they drop off quite sharply after you get above 100 milliseconds in this case. Now, the other thing we looked at is what happens if we have lots and lots and lots of parallel bottlenecks at once. How does that affect the efficiency? And we find out that the RFC version, after we get above 4 parallel bottlenecks, starts to sort of drop off in its accuracy. The dynamic clustering method that we have improves on that with the summary statistics, and the cross-correlation wavelet filtered methods are pretty straight regardless of how many parallel bottlenecks we have. So in conclusion, RFC 8382 performs pretty well. It's simple, it's light, it's really fast compared to all of the others. It handles path delays well. Summary statistics introduce a lag, so that slows it down in detecting and undetecting. And if you have high numbers of parallel bottlenecks, then a different grouping mechanism, such as the one that we proposed here, improves on that. Now, a limitation of all of these methods, and all shared bottleneck detection methods, is they assume that bottlenecks have measurable similarities and all flows sharing them, a sort of a bottleneck signature. And a counterexample is that if your sending pattern dominates a bottleneck, then what you end up correlating is sending patterns rather than a bottleneck signature. And that potentially in some circumstances can mean that you group flows together because their sending patterns matched, not that they were sharing a common bottleneck. So the path forward, we think that for a proposed standard to be useful, then that limitation should be addressed first. And addressing it may be algorithm dependent. So it may depend on whether you're using Scream or whatever, and you may have to have that knowledge. A generic algorithm may be possible using the ideas of sort of a speakerphone cancelling out feedback. So you may be able to do it that way as well, but that requires a bit more research. Or the other thing you could do is just note that it's happening, and then when it's happening, treat your SBD results accordingly. And we're calling on any interested parties to continue this work. Thank you.
Okay, thank you, David, for the update on SPD. Do we have any quick questions for David? Otherwise, it's nice to see that the standardized version still looks to be performing quite well in your evaluations.
Yeah,
So,
it's very simple and light comparatively. Once you go to clustering, it's a lot more CPU to do the work.
So David, did you look at more complex layer 2 bottlenecks where you've got some sort of algorithm going on underneath to allocate bandwidth, and the bottleneck kind of is changeable and maybe not characterizable? Did you actually manage to touch on any of that aspect when you were doing your exploration and thinking?
Can you just explain a little more, because I'm just trying to picture what you're...
Sure. So I'm thinking about a radio link that's actually doing some sort of adaptive bottleneck, adaptive bitrate method, maybe to counter rain fade or movement of the parties, and then your bottleneck doesn't fit any mold, and presumably you have to kind of reject this one as being difficult to characterize. But did you think about these kind of really odd ones that also appear?
I can't say that we've thought that much about that one, and that has the same sort of limitation. Except in this time, instead of the sending one, you have this other pattern being introduced. So you have to have some way of filtering that out so you're able to compare it. And at the moment, all detection methods have this same problem.
Yeah, I really enjoyed your feedback. So that was a super presentation, and look forward to hearing more when other people advance this thing.
Okay, excellent. So thank you very much, David, for that update. I don't see anyone else in the queue, and I think we also need to move on to the next presentation. So Colin, you are up next.
All right, I can make this share slides. Okay, is this working?
Yes.
Yes. Okay, so hi, I'm Colin Perkins. I'm going to talk quickly about some of the overheads of congestion control feedback in RTP, which is the final working group draft we have in this group. So the goal of this draft is to outline some of the overheads of using the various congestion control feedback packets that we've defined in this group. So it's looking at the RFC 8888 method, and applying this along with the other types of feedback you get, the various compound and non-compound packets, the different feedback profiles, the different reporting extensions, and so on, to try and sort of work through the calculations and show what sort of overhead you get from sending congestion control feedback in some typical cases, so people can sort of get an idea of what's the cost of doing congestion control, and what are the factors that influence that cost. So it looks at two relatively straightforward cases. The first being the voice over IP case, and the second one being a simple point-to-point video case. So in the voice over IP case, we're looking at a two-party voice call, sending frames, so many voice packets per second, and wanting to send congestion feedback either every frame, every second frame, or so on. And we're trying to set the RTCP reporting interval, so we're sending RTCP reports every few audio frames, maybe every second frame, every fourth, every 16th frame, or whatever. And obviously, there's different ways of configuring RTP and RTCP, and we can send the reports, the feedback reports, either as regular compound RTCP packets or as non-compound packets. And we can mix and match between these. So we can either send compound packets every time, or we can send compound packets with non-compound packets between them. So the draft works through the format of a bunch of these packets. So it starts by looking at the format of a compound RTCP feedback packet, and it sort of looks at the size of the various headers. So it says if we're using UDP and IPv4, you've got a certain size of header, you've got a certain size of header and overhead for the sender reports, a certain size of source description packet, a certain amount of congestion control feedback packet, the SRTCP authentication tag, and so on. And I'm not going to talk through all the numbers here, but the draft works through sort of counting, the number of bytes in each of these to figure out the packet sizes. And it does the same for the non-compound packets, which just send the congestion control feedback report and don't have the other RTCP packets stacked in there. Obviously, you get a much smaller packet because you don't have the source description packets and the sender reports and so on. A real system would then send a mix of these, so it has to send occasional compound packets in order to keep RTP working, because you need occasional sender reports and source description packets. And then in between that, it will send non-compound packets that are just sending congestion control feedback to reduce the overhead. And obviously, you can change the balance between these, and what we're seeing on the slide is something that sends one compound packet followed by a couple of non-compound packets in a repeating pattern. And in some cases, you could just send the compound packets, or you could have one or two or three or whatever non-compound packets in between. The draft then sort of looks at how you do the calculation to figure out the overheads, and it goes through the RFC 3550 reporting interval calculation, and shows that the reporting interval depends on the number of participants in the session, the average size of the packets, the RTCP bandwidth fraction that's been allocated, and that lets you work out the RTCP reporting interval. If we want to send a congestion control report every a certain number of frames, you set the reporting interval to be that number times the framing interval, and you work through the maths, and that gives you a fraction for the bandwidth overhead that you'll get if you want to send RTCP reports at that particular rate in order to get congestion control feedback. And the core of this draft is a bunch of charts showing the overhead in various cases. And so, for example, in the case where you're sending only compound packets and you're not using any of the non-compound packets to reduce the overhead, this table shows that if you have your audio being framed into 20 millisecond packets and you're sending RTCP feedback every second frame of audio using only compound packets, your RTCP bandwidth is 57 kilobits for the congestion controlled feedback. And as you increase the number of frames, if you report every 8th frame, this drops down to 15 kilobits. And if you if you increase the audio framing interval, then the overhead drops down more. Again, this is only sending compound packets, but it's showing that you can adapt the overhead of the RTCP congestion control feedback by changing how often you send feedback and the size of the audio packets. If you do the same thing by sending compound packets in between, and this is alternating compound and non-compound packets, you see the overheads reduce somewhat, and if you send more non-compound packets in between, you can reduce the overheads further. And it's showing the sort of example behavior you get as you play with the different parameters to illustrate what the overhead of these mechanisms is. It then does the same sort of calculation for a point-to-point video conference, assuming we've got 2 people both sending audio and video streams, all bundled onto a single 5 tuple. So you've got 4 active SSRCs, 1 audio, 1 video for each of the 2 participants. And we're trying to send congestion control feedback every so many video frames. The sort of feedback you get in this case, you've got your UDP IP headers, and you've got, because there's 2 SSRCs, you've got the feedback being aggregated into the packet, and you've got 1 compound RTCP packet from the reporting source, 1 from the non-reporting source, assuming you're using the reporting groups and the aggregating feedback mechanisms, and then you've got the authentication tag for SRTP. And again, I'm not going to talk about it in much detail, but the draft works through this. The non-reporting packet has, assuming we're only sending compound packets, has an empty sender report, source description, CNAME, and the reporting group source packets in it. The reporting source has a complete sender report. It has the SDS CNAME and the reporting group packet, and it's got the congestion control feedback. And because you're using reporting groups, this is the congestion control feedback for both SSRCs, since they're co-located and are seeing the same thing. And the draft works through counting up the size of these various packets and figuring out what the overhead would be. That turns out to be quite large in this case. You've got a lot of overheads because of the SSRCs and the various reporting packets. You've got a couple of 100 bytes overhead plus the feedback. And it works through and it does the same sort of calculation, plugging in the numbers into the RTCP reporting interval calculation from 3550. And from that, it comes out with a table showing the bandwidth overheads. And what we're showing here is if you look on the left here, the media rate column, it's making a bunch of assumptions about how the video is packetized, which are not entirely realistic, but are probably close enough to give a flavor of how this would work and make the maths tractable. You know, if, for example, you're sending media at 200 kilobits per second, and 16 frames per second video, then that gives you, and you're trying to send a report for every frame, that gives you one video packet per report, probably 3 audio packets per report, depending how you do the audio packetization, leading to an RTCP bandwidth of sort of 67 kilobits per second, which is about a third of the video rate. And as you see, as you go down the table, as the media rate increases, the overheads of the reporting go down, and the table shows how this varies with the frame rate you're choosing and so Similarly, you can use reduced size packets by playing with the way you configure RTCP, and I'm not going to walk through the details, but the draft does that, and it shows that the required bandwidth drops down as you might expect, and reduces the overheads. So that's the sort of very quick version of what's in this draft. The latest version of the draft, what I've done in this version is brought the calculations up to date with the published version of RFC 8888, corrected a couple of minor mistakes in the way the calculations were being done, and the previous versions had placeholders for multi-party and screen sharing scenarios. I've taken those out because when I tried to work through them, I just realized there were way too many variables to easily characterize it. And if I wanted it, if we want something in there which would actually be representative of the different ways of configuring it, this draft is going to balloon out to 50 pages long, and it didn't seem worth the effort, because the scenarios in there, I think, illustrate the fundamentals of the behavior. So that's where we're at in this version. As I say, it illustrates the various factors that influence the overhead of using this congestion control feedback, and I think hopefully gives some useful hints to implementers how you might configure and use the format. From my point of view, I think this is done. It's got everything I want to put in it. And I think it illustrates the point. So my recommendation would be that if the group thinks this is useful enough to publish, we should take it to last call. If there are nits or details to sort out, we can do that. But if the group thinks that there is significant, if the group thinks that it needs significantly more work to get this into a useful state, I'm not convinced it's worth, to me, the effort of doing that. So that's where I think this is at. With that, I think I'm done.
Okay, thank you, Colin, for the update. Do we have any questions for Colin? Yes, Jonathan?
Throw the question back at you. Do you think it's useful in its current state for implementers? Is this something
sorry, you're breaking up and I didn't hear that.
do you think this is useful in its current state for implementers?
I think it's useful, yes. I mean, it's obviously only covering some of the basic cases, but I think it shows the point of how to configure things. But
does it give enough guidance that if you have a specific, more complicated case, somebody could follow the same procedures you did and get an answer?
I think it illustrates the general principles, and in the more complex cases, there are so many different parameters to configure that it's hard to give specific guidance.
Yeah, but somebody who knew what their parameters were could, follow your procedure and say, okay, for my case where it has this and this and this and this and this is what I need to do. Probably.
I think probably. I mean, obviously, it would depend on their experience with RTP and congestion control and so on, as to exactly how familiar they were with the various things.
Okay.
And this is, of course, an informational document.
Right. Yeah, it's targeting informational.
Do we have any more comments or questions? If not, I think we are also, in a sense, this is also moving us into our last item on the agenda, that we have a few minutes to see how to wrap up and what our outstanding work points are. And of course, this draft that Colin just presented is our last open working group document that we had not concluded. And from the author's perspective, this draft is complete. So the suggestion here, I think, is to send it out for working group last call and feedback from the working group. And there, of course, it's very good to get feedback on the current status of the document, and if you see that this is a good piece of advice to publish from the working group. It now was a while since we talked about this document, and I'm not sure if the participants have had time to read it. So I think that we have to take it to the list to get more feedback on that point. The other thing that we have done today, of course, is to try and have an update and summarize the status of the different congestion control algorithms, because we had on our charter to move some of the one or several of the algorithms to propose standard after experiences. But I think we have it's nice to see that there is some work on some of the algorithms, but I think from the shares perspective, the conclusion is that we have not had enough activity and work that it makes sense to bring any of the algorithms on that path at the moment. I think what we maybe need to discuss is the SCREAM side, because I think this is the algorithm that has seen most use, and as you had on your slide, Ingmar, to have an update that brings in the handling of ECN may be something that is useful still as an experimental algorithm, I would expect in that sense. So we are now also open to have comments on any of the open points from the rest of the participants and what your view is. Yes, ahead.
I was just going to repeat some of the things that Anna said, but let's hear from you, Lars. Go ahead.
Hey, sorry. So I basically think that last remaining document should be AD sponsored, and the group should probably close.
Last remaining one being the mine, or being the SCREAM update?
The one that's adopted.
Okay.
Am I wrong that there's only one adopted, right?
So the one I presented, which has been adopted, and then there was the potential update to SCREAM that Anna was talking about.
Oh yeah. I would just close the group. I mean, if people want to update SCREAM, that can also be AD sponsored. It can be in transport TSWG, right? I don't see a reason to keep the group around. But that's me personally, with no dots or anything.
So I think for the open document, the hope was that this was very close to being done. I guess the document can still move, but just understand what you were thinking there, Lars.
I mean, for my draft, I don't expect to do any more work other than fix some typos that people point out. If it's more than that, I'm going to abandon it.
I mean, the document's basically been around for like 8 years or so, right? And it's occasionally getting updates, which is great, but you know, I would either sort of start working group last call now, or make it AD sponsored.
Martin.
Yeah, just to add to what Lars said, for Scream BIS, 8382 BIS, it is an experimental document, so we could actually even do it in ICCRG if that's a better venue for it.
Corey?
I wondered if there were still enough people around Mcat to review Colin's document, whether people were willing to give the final version a read, and therefore whether you could do a working group last call. Do you have any sense of how many people are ready to read it?
So that is a bit hard to judge, but I see that Jörg at least is willing to read it in the comments in the chat. We have about 30 people attending this session. So, and I think it would be very good also, of course, if some of the algorithm authors can also read it. So that would be my hope, but it's always hard to assess, of course. Ingmar also says he's willing to read it, so I think that would be very good. I think we could also check if, I'm not sure if Xiaoxing is in the call. I know she's still in the mailing list, even she has moved from Cisco. If she is also willing to read it from the NADA side. So I think if we keep it in the group, the idea, of course, is to move it to working group last call and to try to finish it up. Yes, Sahid?
I hope you can hear me.
Yes, we hear you.
Yeah. So I mean, with my Eddie hat on, I think I have not seen any huge activities or any activities in the mailing list, and I have not seen, like, I mean, NADA, as you reported, 2020, it has implemented a Firefox Mozilla. I have no information on whether that is used. Scream, Ingemar is doing some trials, and that's good to have, and we can actually fix some updates and all these things. So that's fine. Other than that, I don't see like anything happening. On somebody, I mean, previously in one of the IETF meeting, there was one proposal coming from, like somebody asked, like, can we make another congestion control algorithm and all this thing. I don't think like they're coming back. So and today from this meeting, I get a view like, well, there might not be too much energy to carry the working group on. So I think for this document, the last document, that working group document we can go directly to the working group last call and push it to IETF last call very soon. Other than that, I cannot convince myself like why we should have this working group. And if we need, we can actually keep the mailing list alive, right? So if there is anything, some people want to come in future or some updates want to be discussed, this mailing could still be there. So that's actually what I think. Mm-hmm. And yeah. I think this working group has produced a really good documents. I have been part of this working group from very beginning. It was a quite good journey, but I would love to see this work has been deployed and adopted. Other than that, I don't see any output from this working group.
No, so as I said, I mean, we had decided to have some pause to see if there would be more deployment and experience from the algorithms, but as I said, as shares also don't see that any of the algorithms would be, candidates to be pushed forward at this point. So that part of the charter, I think, is not relevant at this point in time. So I think we all have the same view on that. Yeah, I see one more +1 for doing a working group call, last call on the document. So we can, of course, also coordinate on how to wrap up that last document. If you have other comments on that one, Said, but otherwise, I think the plan is we try to finish off the last document, and then we are ready to close the group. This is my understanding of the situation and the sense of the group as well. And we are a little bit over time, but Gori, you are in the queue. You wanted to add something?
Yeah, I just wanted to say I have put the names of the people who volunteered to contribute to the last call in the notes, so that they're now in the notes.
Okay,
Thank you.
excellent.
Yeah, then we have an agreement there and way forward. So let's do that.
Okay, great. Then thank you everyone for today, and it was still very nice to see you all and to also get an update on what was ongoing with at least some of the algorithms. So anything you want to add, Colin?
Mostly I'm going to add that I still can't work the mute button. I was just going to say thanks everyone for participating. As you say, it was good to get an update and come to a closure on the group. And yeah, we should try and get that working group last call done very quickly, I think.
Okay, thank you all.
Okay, bye.
Bye-bye.
Yeah.